Thank you for staying until the last talk, or maybe you stay for the party. Might be different reasons. Yeah, we're going to talk about garbage collection at 5 p.m. It's going to be fun. Nice to meet you all. It's the first time that I'm in Porto. I'm Anna, currently working as a developer advocate in the Java platform team at Oracle. And I'm passionate about working with Java and Kubernetes. Hence, today's talk is combining the both. A bit of the agenda of today, sorry, before going to that. We're going to go through a little theory. We are going to also see why does choosing a garbage collector matter, so why not stay with the defaults maybe, in which cases we shouldn't stay with the defaults. We're going to look at the setup that I used to test different assumptions of mine about tuning the garbage collector, and of course discuss the ergonomics of serial, G1GC, parallel GC, and generation ZGC garbage collectors. So, in Java, we pretty much love garbage collection because it automatically frees memory for us, unlike maybe in other programming languages that we've tried as developers in the beginning when we're beginning with object-oriented programming, where you just needed malloc, salloc, and all this, and you had to like think about your algorithm, but also on how memory is being allocated to that and how you're going to handle that efficiently. But no, Java is doing this for us. Now, in Java, garbage collection means that a garbage collector tracks every object in the JVM heap, and it removes unused objects. That's pretty much the simple definition of garbage collection. But it essentially does 4 operations. It allocates objects on the managed heap efficiently, and it reclaims no longer used objects, clears their memory, keeps the memory available for future allocations, and that is great for us as developers. Now, can you please raise your hand if you heard about generational garbage collectors? Okay, so we have a few people that have heard about it. So the generational garbage collectors, which are the current garbage collectors that we have in the recent distributions of the JDK, including JDK 21, are based on the weak generational hypothesis, which states that the young objects tend to die young, while old objects tend to stick around. So, as we know, well, garbage collection will primarily focus with the reclamation of the short-lived objects. Now, newer objects will have shorter lifetimes, and older objects have longer lifetimes, obviously. But newer objects that tend to be related to each other and accessed by the application around time, they will stick around and age a bit through that. So how does generational garbage collection works? Well, we have a few spaces. Like newly allocated objects are getting into the young spaces. Data being partitioned in multiple allocations or regions, call them generations, which are kept separate based on the object age. In the young region, well, is the heap region that contains the newly allocated objects. So you have their newly created objects, new objects that live beyond one garbage collection cycle, and objects that survive a few garbage collection cycles and get moved between the survivor spaces. Now, the old region, well, if an object gains enough age by surviving a few GC cycles, it will be copied to the old region. And of course, in the permanent metaspace region, the final region where there is typical JVM metadata, core system classes, and other data that typically tends to exist for the entire duration of the JVM life. So, just to give an example, if a new object or new objects are being created by our application, they are added to the hidden space. When the first garbage collection cycle gets in, these objects are moved from Eden to survivor space 1. At the second garbage collection, when the age would be 2, the live objects are moved from Eden to survivor 1. So of course we're going to have new objects. They're going to be moved as well from Eden to survivor 1 and from survivor 1 to survivor 2. So this happens with the age of each object. Now, at the nth garbage collection, the live objects are moved from survivor space to old region once they gain enough age. So, these are a little bit important to know, like how the objects travel to different regions within the garbage collection. So now let's look at why does choosing a garbage collector matter. First of all, you need to determine your context. The garbage collector, they strive to be as optimal as possible for every aspect, meaning there are a few different, there are some trade-offs, and of course that support different use cases, and we're going to look at them with each garbage collection. But first thing you need to ask yourself as a developer is, like, if you get enough performance with the garbage collection default settings that you're probably using in the beginning when you start an application. I don't think anybody starts tuning an application or the garbage collection of an application just from the beginning without seeing the default maybe satisfying their cases. Then if the GC pauses are enough, they support our application goal. So we can look at that. There are a few metrics also with micrometer that can be inspected later on in Prometheus, and see if the GC pauses support our goal for latency or our goals for throughput, for example. And last but not least, can your application tolerate different settings for GC pauses? If that is the case, then maybe we can alter those and some other parameters. Now, there are a few performance considerations that probably you have within your application, like throughput, latency, and of course, footprint. Meaning, you'll probably want to have as much throughput as possible, like have a lot of successful transactions within your application at the lowest latency as possible, and of course, the footprint, like consume as little resources as possible. Now, that's the dream of everybody. However, you have to make some concessions throughout time on which matters for you most. And matters for you most actually matters for your end users most. So let's take some examples. First of all, let's think about our applications. Are they CPU intensive or IO bound? So what does that mean? A lot of people are not aware of what that means, or like which trade-off they should insist on when it comes to their application, because based on that, maybe garbage collection would tuning garbage collection based on that trait, it would help them more. So the CPU intensive examples, and you have them here in the slide, represents a type of problem that requires a lot of processing power to solve. Usually the mathematical problems like performing complex mathematical calculations, or rendering graphics or videos, or encrypting or decrypting data, or anything that deals with security and it requires a lot of compression and so on, that's CPU intensive. Now, on the other hand, the IO bound means that a given task often awaits for IO. So networking, file IO, and so on, they are considered as IO bound examples. And you also have some of those here, like processing systems, usually web applications backed up by a database are kind of IO bound examples, video editing, downloading files, and so on. So let's look at the setup that I have for my application. Now, in my case of my setup, I had chosen for two applications. They don't use any framework, so they're pretty plain Java applications. I just created Java applications that use the HTTP server, and inside them, I have just added the dependency to Prometheus, to micrometer, to export to Prometheus some metrics further on, so I can query. So I kept them at minimal. Now, the first application, the Eager Factorial, as it says, it makes some very, very big math calculations. It computes big factorials with big integer. Takes a lot of CPU for that. And of course, the second one is the continuous editor that continuously edits a file. So that one is, I'm going to look at it from the IO bound perspective. Of course, I need to test these, like to see like how they behave with different garbage collectors. What traits can I improve throughout time? So since I'm containerizing, deploying them in Kubernetes, I thought to use TestCube for that. And TestCube gives me the opportunity to have a test orchestration and an execution framework for different kinds of tests. So you have like a series of tests you can execute against your application. In those executors, there's also K6. So I've chosen K6 tests to do this setup. The reason why I did it, because also K6 can be run on local, so the same tests can be run on your local. However, you can still run them on in Kubernetes, and I would say you get more reliable results than putting your laptop to stress running the applications and also the tests in the same time. Now, of course, we need to observe the results. So For my applications, I've measured throughput using the app request duration seconds count and sum by each instance of my application and look at the rate of that. Now, that metric is something that I created for my application because it's a simple Java. Both of them are simple Java applications, so I needed to instruct how am I going to look over the throughput of the app in that case. In case that you're using frameworks, those usually get translated to a different metric. You can ask me after the talk, and I can tell you which ones are for Spring Boot and Quarkus, because I've tried those quite a while. Now, for latency, you need the rates division over the duration second sum over the count. All the time, the interval in my case is going to be 2 minutes. And next one, I'm going to look at the CPU, the process CPU seconds total, and the average over time of the JVM memory bytes used over the same intervals all the time. Now, 2 other metrics that you can look at while you observe all this, but I will not share that in the slides, for monitoring the garbage collection would be to look at the JVM GC collection seconds count to see the number of garbage collections that occur in a certain interval of time, and of course to look at the duration of these garbage collections that occur in a specific interval of time. Now, that's useful to look into how much time it takes per generation. So you can look at that by each generation in that given interval of time and see which generation takes longer to be garbage collected, or how's the age of the objects there. And since we talked about tests, what do the tests contain? So the tests contain, I could have done 2 types of tests. However, when you're trying to assess, let's say, what would be better for your system and look at the performance, I would suggest to start with average load testing. And ideally, you start having in mind a specific number of users of your system. Like, either you get this from the business, either you have some tools like analytics tools that provide you the information from production environments about how many users your application kind of has in average. In my case, I established that my target user number is going to be 80. Like, in average, I want to have 80 users. These users will try to do as much as possible with my application, so they are not limited to do 1 request towards my application. They can do as much as possible towards a specific endpoint in the given duration of the test. Now, speaking of duration, how those durations translate? First, you start with a ramp-up period, because this period, well, is essential to give you the system time to warm up or to auto-scale to handle specific traffic. But also it lets you compare specific response times between the low load, when it starts, of course, at 0 users, and when it gets to 80, in like average load stages. Usually, this kind of duration, you would say, like, to be between 5 or 15% of the total test duration. So this is why I chose like 15 seconds for my tests. I know that they're pretty short, and in reality they would last longer, but I needed instant, let's say, instant results for my test. Then 90 seconds, I'm going to keep my users at 80. So all the time, 80 users are going to try to do as much as possible with my system. And then after that, during 15 seconds, the system has time to get to 0 users. So the amount of requests will decrease. Good. Now, in case of any Java application, it starts with a few defaults, including for the garbage collection and memory. So, if you're looking in the JVM ergonomics, the JVM will make decisions on certain defaults based on your operating system, based on how much memory and CPU is available. So, for example, the serial garbage collector is being selected as the default garbage collector if you have 1 CPU available or less than 1,792 megabytes. In case you have 2 processors or more available memory, the G1 GC is the default. Initial heap size will be 164 of physical memory, and maximum heap size will be 1/4 of physical memory. So these are the defaults, and sometimes the defaults work great for the applications. However, it doesn't hurt to look into improving that. because I've given this talk before, and some people ask, like, why don't you touch the serial garbage collector? I thought of like talking about it a bit as well. So serial garbage collector performs all the collection on a single thread, has a higher pause time, but it has lower resource usage, so it's great. But it is best suited for applications that either use multiple threads or just run on a single CPU. It's selected by default on certain hardware and operating system, and you can enable it, of course, with a flag. From my experiments, I rarely saw it selected by default. If you want to fine-tune it, so if you're in the case that you are using the serial garbage collector, you can fine-tune 3 aspects about it. First of all, you can fine-tune the max GC pause in milliseconds to provide a hint that the GC pauses should be less than the provided amount. In this case of this garbage collector doesn't have a default set. Some others have. The GC time ratio, to set the time, the ratio of time spent between performing garbage collection work and application work. And of course, to use string deduplication, starting with JDK 18, string deduplication was ported also to serial GC as well. So by enabling string deduplication, you can reduce the memory footprint, sometimes by 10% for your application. But this could impact the pause times of your application, so be aware of that. Okay, so now it's time for a little quiz. This is what I got when I started with the defaults, like no selecting anything for fine-tuning the JVM. This is what I saw in my container, in the logs regarding my garbage collector, 2 CPUs, some memory that is being used. So what garbage collector do you think is selected in this case by default? Sorry? Yeah, it's G1GC. Because the JVM saw that there are 2 CPUs, so it already defaulted to G1GC. However, I've heard about situations when people fine-tune their Kubernetes 1 CPU per container and can be serial, the default one. So, to give a short intro about G1GC, the G1 garbage collector divides the heap map into smaller regions, and, well, the regions which are the most enrichable, where the most enrichable objects are, those are garbage collected first, since those free up a lot of memory. That's why it's called garbage garbage collector. Now, with garbage G1GC, it works great by default, and this is from the documentation. But the garbage first collector is not a real-time collector. It tries to meet some set pause targets with high probability over a long time, but this can exhibit lower overhead throughout time than compared to other collectors. So this can affect throughput to time due to its sometimes concurrent nature. So, given that it varies a little bit, of course I had to start my test somewhere. So, the test conditions that I used, well, in my case, the first test, it was selected by default, and by default, in the first case, max GC pause is set to 200, so the hint that the GC pauses should be less than 200 milliseconds. Now, the test conditions, as said earlier, traffic ramp up from 1 to 80 over 15 seconds, stay at 80 for 90 seconds, and then ramp down to 0. Now, in that case, I got some results. I know it's not going to be seen through back, but I'm going to have a table saying this again. So I'm interested in the average time of the request duration. I'm also interested in percentile 95, like the 95% of my requests took equal or less than the value specified there. P99, the percentile 99 and percentile 99.9, and see how that happens. And of course, the count is going to be the amount of requests that I successfully managed to do. So ideally, I would have as many as possible. Now, this is the result for the eager factorial one, for the CPU intensive one. And these are the results for the one that is IO bound. Now, these are just the first results, so we just need a starting point. It's going to be like the increase of CPU usage, of course, is expected. The one that is using more CPU, you can see that goes like a mountain. Like it spins up and uses a lot of CPU and then goes down. And of course, the memory is kind of comparable for both over time. So next, I need to choose, like, what I want to do. I want to improve the latency, or I want to improve the throughput. Now, if I'm looking over latency, I should think of choosing a different, maybe, pause time. And of course, it would help me in some cases to set the initial heap size and the max heap size with equal values. In order to avoid delays, you set them with the same value. Now, if I want to tune it for throughput, then I should increase the maximum pause time from that 200 milliseconds. Because using that kind of trick, the generation sizing heuristic will automatically adapt the size of the young generation, which directly determines the frequency of pauses. Now, another option to increase throughput, if your operating system allows it, you could use it -xx use large pages flag. That one can also improve the throughput. There are some other flags that can improve the throughput, but I didn't want to go too deep into that one. Usually, I've used these kind of two flags, and I got good results throughout time. So, running the same tests, like not changing anything regarding the tests, just updating some information for my garbage collector, I can now compare a bit the results, like with the defaults and after applying some flags. So by lowering the max pause millis with 50 milliseconds in case of eager factorial, the CPU intensive one, that's in mathematical calculus, and of course setting the memory, I managed to improve the throughput, but I can see that also I managed to have a less latency improvements too. So everything like lowered in the time span of the duration of my requests in average, but also I managed to improve my count a little bit with like 200 requests by updating my my flags. Now, to have a better view, this is how it looks like in the comparison. So in the beginning, I had like 44 milliseconds, but then both the percentile 95, 99, 99.9 improved after adjusting the max GC pause millis and the initial and maximum heap size. So I would say that's a pretty good result. Now, how did I get there, like to those flags? It's a good question, right? So I looked at the defaults, of course, and played a little bit with what is available in the default so that I can determine a max GC pause that could help me improve the performance. So I went a little bit empirical on that one. However, in the case of continuous editor, I felt like I really want to strive for throughput. So I would do the increasing of max GC pause and set, of course, the memory as well. So for this one, I also managed to increase a lot my throughput, as I said, because I managed to increase the max GC pause millis from 200, the default, to 250 milliseconds. And I could see the results that are pretty much relevant on improvements. Also, the latency looks pretty good as well. And here's how the difference is looking good. It's looking for the IO-bound application. So there's this a slight difference with the CPU usage and the average memory used over time, because my conclusions were like, okay, I got better results for latency and throughput, but the memory used decreased for the one that is IO bound. For the other one, it kind of stayed at the same level. So I managed to get a quite okay thing, but as I said in the beginning, you cannot have everything, so you cannot see like a major improvement in CPU usage or a major improvement in memory after adjusting the pause time and setting the memory. However, throughput and latency improved, so I'm happy with that. However, let's look at applying the parallel collector to the same setup. So the parallel collector, also known as the throughput collector, has three goals. the goals of maximum pause time, has the throughput goal, and of course the minimum footprint goal. And it achieves those goals in a sequence. So the maximum pause time goal is the first one that this garbage collector wants to meet. Now, after this one is being met, it looks at the throughput goal to address it and to make it happen, and then looks at the footprint goal. And this throughput collector has two operations: minor collections and full garbage collections happening over there. Now, why it works so great by default? Well, because adaptive sizing in the throughput collector would resize the heap and hence the generations in order to meet the pause time goals. And these goals are being set with the max GC pause millis and the max GC time ratio. So the throughput in this case has like a very nice calculation based on the GC time ratio flag. So you can like have a better control over that. And moreover, the adaptive sizing, well, has also growing and shrinking and of the size of generation done incrementally. So you can also play with these flags if you really like go into more detail of fine-tuning it. However, I didn't want to touch them up to that to observe some results. To set it up, because in my case it's not selected by default, I used first I started like with the defaults and just have it, they use parallel GC and see what's happening with the same tests. So, the results in this case were slightly better than the ones that I had in the beginning with the G1, GC from throughput perspective. I think from latency they're comparable. And in the continuous editor, I think they're slightly better than the defaults with the G1, GC. So the CPU usage, I think it increased a bit, and the memory used, it's a little different than in the other case. So intermediate remarks were that the latency decreased and throughput increased, which is good for that. However, the memory and CPU usage decreased only for the ones that, for the application that is doing mathematical processing. For the other one, I haven't seen much change. So maybe something would be good for that one that does intensive mathematical processing with this kind of garbage collector. Now, if I want to tune it, again, max GC pause millis is going to help me. And of course, to adjust throughput, I'm going to use the GC time ratio because, well, that was in the formula, and I can calculate the throughput that I want based on that. So now I'm comparing again the results. I have managed to improve a lot my latency if you observe this, like from 55 milliseconds to 8.6 milliseconds. But I'm interested in the throughput. So there's a high difference in throughput after adjusting the max GC pause millis. So now that I'm looking at the table with what happened throughout time, I can look at the total requests and which one was better so far, and of course where I got the best throughput. Now surprisingly, the best throughput and best latency, it's on parallel GC with altered max GC pause millis. Once I got this result, and of course I ran the test multiple times to see that it really does this and keeps this throughout time, I was pretty satisfied, and I didn't want to change any other flags of this garbage collector for the mathematical intensive application. For the continuous editor, only setting the max GC pause millis was not enough, so I modified the throughput, the GC time ratio to 99 to actually achieve more throughput in this case. So yeah, I managed to do that thanks to the setting the -XS GC time ratio, and it was quite a great increase. Now if I'm looking at the comparison here as well, you can see the differences throughout time. So the defaults, if you're looking between parallel and G1, GC, of course the defaults for parallel GC do better, even for continuous editor. And also in case of the fine-tuning, it does better as well. However, I didn't manage to get for this one, which is I/O bound, latency that's below 10 milliseconds. So we should investigate some more later on. Okay, so now from the increase of CPU usage and from the memory time used, I could see that, well, for the one that is doing mathematical calculations, Well, it was memory usage lower, but for the other one, memory usage was significantly decreased after changing the defaults of parallel GC. So for the one that's IO bound, parallel GC did more from memory perspective, from memory consumption perspective, not just brought me good throughput and some decreased latency. So just by adjusting this, I managed to get some very good results for a continuous editor, but also in case of the eager factorial one. So let's get to the last garbage collector that I want to talk to you about, the generational Z garbage collector. In case of the generational Z garbage collector, why is it called like that and so on? Well, ZGC, there is already a garbage collector that's called like that. It was initially introduced as an experimental feature in JDK 11, and then it was declared production ready in JDK 15. But at its core, ZGC was a concurrent garbage collector. And in the beginning, we talked about generational garbage collections, right? So what the concurrent garbage collector meant is that the heavy lifting work is being done while the Java threads continue to execute. And this kind of limits the garbage collection while your application has to serve a very nice response time. So hence, observing what's going on with the ZGC, the generational ZGC was introduced. And what this does, it keeps the properties of the ZGC, of course, but also you get lower CPU usage, lower heap room, so you get a reduced effort to collect the garbage. In addition to that, ZGC was kind of famous for not having to tune a lot to work with it. And so the only thing that you need to work with generational ZGC when you need to tune it, you need just the max heap size to set it. So you don't need to set the initial heap size, you don't need to set like some threshold or concurrent GC threads and so on. So this is pretty cool. However, I just wanted to keep it similar to the other garbage collectors. So in the beginning, I didn't set any max heap size for the generational ZGC. By just not setting anything and just running the tests, in case of my first application, I got, let's just say, latency and throughput comparable to what I had with parallel GC without tuning anything. So I was a little bit disappointed about that. For the second one, I could see that the results kind of improved a lot in case of the throughput, but the latency was not at its best. So maybe something better could be done. Of course, CPU usage was pretty much the same. Memory was a lot. So memory consumption was a lot. So this kind of triggered me that maybe I can tune it. So what I did, I actually set the maximum heap size for both applications. So in case of the eager factorial, I set it to like 1 GB, and to the other one, I thought of like setting it to 2,816 megabytes. So let's see the results. In case of the results of the first one, that's CPU intensive, I really got a good spike, in throughput. So, but just by adjusting it, setting the memory, throughput got really well, like almost I think the best in this case. And latency itself was approaching 10 milliseconds. So I was pretty happy to see that both throughput went through the roof once I set the maximum heap size. That's the only thing that makes ZGC working at its best, just the maximum heap size. Now in case of the continuous editor, I did the same thing. I set the maximum heap size. I could see an improvement for the throughput and some improvement for my latency. Okay, so of course CPU usage kind of increased for both applications compared to the default one, and also memory. Well, in case of the memory, I saw that I consumed less memory for both, which was good, thanks to fine-tuning and setting a limit for my maximum heap size. Now let's compare this again. So for the first application that was mathematical intensive, the parallel GC gave me the best throughput and the best latency. So if you're looking on that, I just folded that to be the last. The second best in that case is generational ZGC, with just setting the max heap size there. Next, here I was a little bit worried because the best throughput seemed to be generations DGC. However, percentile 99, percentile 99.9 got better on the parallel side. So I was a little bit confused, like, okay, the difference in throughput was not that much. I mean, like 8 more requests managed to succeed between these two. The generations DGC had a percentile 95 better, and of course an average duration as well. So in these cases, when you don't know which one would be better, maybe it's better to apply a new set of tests to your application. So what I did, I stressed the application, and then in the case of the stress application, to stress test an application, you have to change a few things. Like you need to apply a higher load than you experience in the average. So in the average, I was using 80 users that were trying to do as much as possible. In my case, I said, okay, I want to do 100 users that do as much as possible, but not in the 15 seconds of ramp up that I had before. Do it during 20 seconds, so to have the ramp up on a longer time. But a shorter scale down, a shorter time for scaling down the system, like 10 seconds in this case. So I reused my average load script, which I tell everybody to do, and compared the results. Now, usually when you're doing stress testing, you obtain worse results than with the average load test. So that's something that you should know by default. Stress gives you worse latency and less numbers in terms of throughput. Now, for continuous editor, which was I/O bound, in the beginning, while I'm looking at parallel GC, I got somewhat good throughput and good average duration of my requests. However, ZGC on the long term behaved 1,000 times better. I got like 2,000 more requests than in the case of the parallel GC fine-tuned, and the average duration was almost at half. So on the long term, ZGC performed better for continuous editor. So that was my my founding conclusion. That's where you can find the code and all the tests for it. Thank you for listening to me. I think we have 10 minutes for questions, but yeah, if you have questions, I'm more welcoming it. So, or you can find me at the party as well. Thank you.